Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we are going to look at the class data structure. That is, the definition of objects. So, in this lesson, we will introduce the three-body problem and a simulation thereof. We will then introduce the class keyword and see how this can be used to aggregate related data. And we will do this through member variables within a class. We will show how to declare and initialize instances of classes. We will describe how to access and manipulate the member variables of instances of those classes. We will also see how instances of classes are passed as arguments to functions. We will discuss why using pass by reference is appropriate for objects. Now, suppose we are trying to simulate the three-body problem for stars. Now, each star has a position, x, y, and z, velocities in each of these directions, and a mass. Now, if we were trying to program this up until now, we would have had to create two arrays for Rigel Kentaurus, one for its position and one for its velocity, and another local variable to store its mass. We'd have to do the same for Toliman and Proxima Centauri. So this leaves us with 9 different local variables to interact with. Now, all 3 local variables storing information about Rigel Kentaurus are all related. This is like we had an array where the array variable and the capacity variable are intimately related. One describes the other, and in general, you need access to all of the information about a particular star if you're trying to simulate it. Imagine trying to send all of that information and that of multiple other stars to different functions. We would like to group all of this information together. And the way that we're going to do this is with a data structure called a class. So a class declaration informs the compiler that we are now going to define a new type. Just like we can declare local variables of type int or type double, we can now declare local variables of type body. Now, that is the class declaration telling the compiler that body is now going to be a class or a type that can be used. We now have to define the class. So first we're going to start by having the variables associated with any body, in this case celestial one. Well, the only information that is relevant is the current position of the body, and so this is going to be an array of capacity 3, one for each of the 3 dimensions. And note that we're going to indicate that this is being stored in kilometers. Every body also has a current velocity. And again, this is a 3-dimensional vector array. Finally, every single body will have a mass associated with it, and in this case, it is kilograms. So this class, as it stands right now, contains all the necessary information about a star for the problem at hand, and that is simulating how the stars are going to move through the sky. It does not contain information about which stage the star is at, or the color of the star, or the radius. None of this information is necessary because it is not necessary for the problem we're trying to solve. We're only creating a class that stores that information that we require right now. Each three of these variables in the class body are defined as member variables. They are member variables of the class body. Now note, as a general rule in this course, class names will be capitalized, although if the class is composed of multiple words, subsequent words will be lowercase with underscores between words, and member variables will be suffixed with an underscore. Now, this is only a naming convention and is not required. Recall that reserved identifiers in C++ are prefixed or preceded by an underscore, or they may have a sequence of 2 underscores within the word. So this does not break that naming convention, as we are suffixing the member variables with an underscore. All right, with this declaration, body can now refer to a type just like int or double. But however, rather than int and double, which can only have one value associated with any local variable or parameter of that type, now each instance of any local variable or parameter of this type is intimately associated with 2 vectors of capacity 3 and 1 double. All right, now that we have declared body to be a class, we can now declare a local variable to be an instance of this class. Now, an instance of a class is also sometimes described as an object, hence object-oriented programming. So here we see Earth as a local variable declared to be an instance of the class object. When the compiler sees this, the compiler will look at the class definition and see that it requires 2 arrays of capacity 3 and a double. This means that it requires 7 doubles. So it will allocate memory for 7 values or 7 doubles. The first 3 will be the array position, the next 3 will be the array velocity, and the last one will be the member variable mass. Now, just like everything else, we have to initialize the local variable Earth, and we do that with an initialization that has 3 separate initial values. Again, the member variables will be initialized in the order that they are declared in the class definition. So first we see the first initialization value is an array of 3 entries, and that will initialize the first array, the position. So those 3 double literals will be copied to that location in memory. Next, the second initial value is again an initialization list of 3 entries, which will initialize the velocity array. And finally, we have the mass, and that is the third initial value, and that will initialize the third member variable mass. So after this initialization, somewhere in memory, there is memory allocated for these 7 doubles, and these are the values stored in that memory. Now, we have declared Earth to be an instance of a body, and we have initialized it with 7 doubles. The question is, how do we now access and manipulate these member variables inside this instance of body? Well, we use the dot operator, and the left-hand operand must be an object or an instance of the class. So for example, here Earth is an instance of the class body. The right-hand operand must be the identifier of a member variable of the class of which the left-hand operand is. So Earth is an instance of a body, and therefore, for example, Earth.mass underscore refers to the member variable mass, and specifically, if we were to execute this line, what would happen is it would print out whatever value is stored in that seventh location. So the output would be 5.972 e to the 24. All right, next, how do we access the arrays? Well, once again, we access the arrays the same way. We use the name of the array in the class definition. In this case, it's position underscore. And now we can access the three entries of the array by giving that array the index of either 0, 1, or 2. In this case, I am printing out the position at index 0, and so that will print out the first entry. And that would be the output. Okay, now once the function exits, all this memory that was allocated for this local variable Earth would be deallocated, and that memory would be made available again for other local variables or other required memory. Now, it is also possible to manipulate the values that are stored in the member variables of an instance of the class. So here we see Earth being declared and initialized. We are now running a for loop. The loop variable k is initialized to the value 0. And so now we will execute the loop body when k is equal to 0. Well, we are referring to the position and the velocity of Earth at index 0. So we are referring to these two positions, and we will add onto the position at index 0 0.1 times the velocity at index 0. Well, in that case, since the velocity is 0 in the x direction, nothing changes. All right, so now we increment k, and now we access and manipulate the position at index 1 using the velocity at index 1. So now we have 0 plus equals 0.1 times the velocity at that index, and so now we update the position to be the velocity times 0.1, which is 1.07 times 10 to the 4. All right, we're done that iteration of the loop. We increment k again, and now in the z direction, there's no velocity and there's no offset. The Earth is in a plane, or is rotating in a plane, and so we have 0 plus equals 0.1 times 0, which makes no change. Okay, we're done. We increment the value of k. The condition is now false, and we have finished executing this loop. Now, the initialization of local variables of an instance of a class also works similarly to how they work with local variables that are of type double or of int. So and assignment similarly. Here we have Earth and Mars initialized with the data that is shown there. So those literal doubles would be copied to the appropriate positions in memory for the member variables of those two instances of a body. Next, however, temp is declared to be an instance of a body, and it is being initialized with Earth. So what this does is temp is an instance of body. It has 7 doubles, and Earth has 7 doubles that describe it. So each of the member variables and the values stored there will simply be copied up into temp. So temp is now a copy of the Earth. If temp is assigned the value of Mars, this is more or less the same as before. Temp has 7 doubles as 3 member variables, and all of the data in Mars will be copied over to temp. So now temp is a copy of the local variable Mars. But again, it is a distinct copy. It is not Mars. It is simply being assigned all of the values stored in Mars. So if, for example, I assign to temp.mass the value 0, that's only going to assign this particular member variable associated with temp. It will not change Mars or Earth. Instead, it will only change the member variable mass associated with the local variable temp. Next, objects can also be passed as arguments. So here we see a function called speed, and it takes an instance of a body as a parameter. So A is the parameter, and when we execute speed, passing it a body as an argument, then it will simply calculate the square root of the first entry of the velocity squared plus the second entry squared plus the third entry squared. And this is what's going to be returned. All right, so now we're going to look at an example where we actually call the speed function with an instance of a body as an argument. So here we have Earth declared to be a body, and it's appropriately initialized. We then call speed on that instance, and it will calculate the speed, which in this case is the square root of 0 squared plus 107 times 10 to the 3 squared plus 0 squared, all square rooted, which will just give us 107 times 10 to the 3. All right, and that is the value that Earth speed will be initialized with. I'm now declaring a constant that gives me the conversion factor between kilometers per hour to miles per second, and that value is provided here. We're now going to output a little song that some of you may be familiar with, where we will print out the speed of the Earth in miles per second. So the output is, if we would add some music to this, that's orbiting at 18 miles a second, so it's reckoned, round a sun that is the source of all our power. I'm not here to entertain you. So, carrying on. All right, now let's look at how the call stack works with respect to function calls when arguments are objects. So inside main here, before Earth speed is initialized and speed is called, there are 2 local variables, and thus these are located on the stack as shown below. When speed is called, the argument, Earth, is actually copied over to a new instance of the class body. So a parameter of type body is created. It occupies 7 doubles, or 7 times 8, or 56 bytes, and all of this information is copied over from the Earth instance of the class. When the calculation is made, the return value is copied back onto the stack, and this is now returned. Back in main, the return variable is then copied to the location for the earth speed local variable, and it is then used in the subsequent cout statement. Let's see how this works. First of all, in main we have three local variables: Earth, Mars, both of which are initialized, and then we have the local variable Earth, Mars, which will be initialized with whatever is returned by the call to center of mass. Now, when we call center of mass, the compiler will ensure enough memory is allocated for the two parameters A and B, and the local variable center of mass, or COM. Now, all the values stored in Earth are copied to the parameter A, all the values of Mars are copied to the parameter B, and then inside the function center of mass, it will then calculate the center of mass, filling up the local variable COM, or center of mass. Now, when the function is ready to return, it is the object or local variable COM that is being returned, and so that will actually be copied to the top of the stack, or at least the bottom of the stack, for the call to center of mass. Then, when it returns, the values that were in COM will be used to initialize the values in Earth, Mars. All right, now that the function returns, we're back in the main function, and now we will print the information about the center of mass between Earth and Mars. Now, you've probably already noticed this problem. Every time an object is passed as an argument, there's potentially a significant amount of copying going on. Even the arrays are being copied, so that can become very expensive. The solution is to use pass by reference or pass by constant reference. Now, for example, the center of mass function could have both of its parameters being passed by reference. In this case, they should actually be passed by constant reference, because there's no reason the center of mass should change either of the two arguments. It's simply using the information in A and B to determine the center of mass of these two objects. Consequently, inside the body of the function, anytime you refer to A or B, you refer to the actual arguments and no copies are made. This makes life a lot easier. Now, in this case, the return value is still returned by value. Now, following this topic, you now are aware of the class keyword and how a class can be used to aggregate related data. You also know how to declare and initialize objects or instances of classes, as instances of classes are also known as objects. You know how to access and manipulate the member variables of objects. You know how to pass objects to functions and how pass by value works. You also understand that passing by reference is probably much more appropriate for objects, and that it works the same way for objects as it does for primitive data types. Here's the references, the colophon, and a disclaimer. Cheers!